Have you ever really stopped to think about how we get oil and gas from miles and miles underground? It's kind of wild, because it's not like there are big underground lakes of this stuff. It's actually locked inside what's pretty much solid rock. So today, we're going to dive deep into the hidden world of microscopic physics to understand the invisible forces that trap these resources and why they have such absolutely massive real-world consequences.
Okay, so let's just start with the main question, right? How in the world do you get fluids out of solid rock? It sounds totally impossible, kind of like trying to get water from a stone. And you know what? In a lot of ways, it is.
I bet the first thing that pops into your head is, squeezing a sponge. You put pressure on it, water comes out. Super simple. Well, you can just throw that idea right out the window. That analogy completely falls apart when you're talking about what's happening deep underground. To really get it, we need to think much, much smaller. The reality is, it's a microscopic battle. Seriously, it's like a tiny war being fought between different fluids. We're talking oil and water, and the rock itself. And the whole thing is governed by these incredibly powerful, invisible forces. Understanding this tiny battle is the key to, well, everything. So, to get a handle on this huge geological process, we've got to start at the molecular level. We're going to explore the forces at what's called the fluid frontier. This is the molecular battleground, where oil is either won or lost for good. Let's start with fluid tension. Okay, so think about it like this. Inside a drop of water, all the molecules are getting pulled on equally in every direction by their neighbors. But right at the surface, there's an imbalance. They get pulled inwards, and that creates a kind of skin. We call this surface tension when it's between a liquid and air, and interfacial tension when it's between two liquids that don't mix, like oil and water. Now just look at those numbers for a sec. The force between water and air is more than twice as strong as the force between water and oil. That difference in strength, well, that's a huge piece of this puzzle. All right, so we know fluids create these tense boundaries with each other, but what happens when you introduce a solid surface, like, the rock in a reservoir? Which fluid is actually gonna stick to it? This all comes down to the science of wetting, and it's basically a molecular tug of war. If the adhesive forces, that's the attraction between the liquid and the solid, are stronger, the liquid spreads out and wets the surface. Think about water on a clean piece of glass. But if the cohesive forces, the liquid's attraction to itself, win out, it beads up and pulls away, just like mercury does. And this right here is the absolute core concept in a reservoir. Is the rock water wet or oil wet? The answer to that one question determines which fluid is going to cling to the rock grains and which one gets forced through the middle of all the tiny spaces. It fundamentally changes the entire dynamic of how anything can move through that rock. So we've got these forces. Now let's see how they actually play out inside the rock itself. This is how these tiny, tiny pores can become both superhighways and inescapable traps. It's so important to get the right picture in your head here. A reservoir rock is not a solid block. It's more like a super rigid sponge filled with billions, literally billions, of tiny, interconnected pores and channels. This whole network acts as one single, massive, and unbelievably complex capillary system. So here's how that capillary action works inside this crazy system. First, you get the pull. The wetting fluid, let's just say it's water, sticks to the pore walls. That adhesion is so strong, it actually causes the rise, drawing the whole column of fluid up into these microscopic spaces. It's powerful enough to defy gravity. And finally, it all finds a balance. The fluid stops rising when that upward pull of tension is perfectly equal to the downward weight of the liquid. This is the force that can suck water deep into the rock, and it sets the stage for everything else that happens. Now, these forces don't just move fluids around, they're also what traps them. And this brings us to the fundamental reason why you can never, and I mean ever, get 100% of the oil out of a reservoir. The very first thing that gets left behind is something called conite water. See, most reservoir rocks are naturally water wet. That means from the very, very beginning, a super thin film of water coated all the little rock grains. And even after millions of years of oil migrating in and filling up the space, that original water film is still there, stuck to the surfaces. This leads to what's basically a point of no return. It's called irreducible water saturation. The film of water gets squeezed so thin that it actually breaks apart, leaving behind only these tiny, disconnected rings of water right where the rock grains touch. And this water is physically trapped. It cannot be moved, it cannot be displaced, no matter how much pressure you apply. It's now a permanent part of the rock's internal architecture. And the consequences of this are huge. I mean, the source material puts it perfectly. Because that water is always taking up space, it acts like a permanent roadblock inside the pores. And that means the pathway for oil, what we call its permeability, can never be 100% open.
Okay, so that explains the trapped water. But what about the oil itself? I mean, if you're pushing water in to force the oil out, why doesn't all of it just come along for the ride?
Well, here's how the oil itself gets trapped. It's a pretty cool process. First, you flood the reservoir with water to push the oil out. But because the rock is water wet, that water just creeps along the surfaces and it ends up bypassing these long threads of oil that are flowing in the center of the pores. And then, and this is the crazy part, that powerful interfacial tension we talked about earlier causes those oil threads to snap apart, just like a rubber band breaking. And just like that, the oil becomes trapped as little isolated globules, completely stranded in the pore network.
And that is what we call residual oil. These are the disconnected blobs left behind that are physically impossible to recover with our usual methods. They are locked in place by the exact same capillary forces that allowed them to get into the rock in the first place. Okay, let's bring this all together. Why does mastering the physics of these tiny, microscopic forces matter so much? Well, it's because they scale up directly from molecules all the way to macroeconomics. And here's the main reason. Engineers and geoscientists, they build these incredibly complex computer simulations of these underground reservoirs. If they have any hope of accurately predicting how much oil and gas they can actually get out, their models have to account for every single one of these interacting forces that we've been talking about.
So, what are the big ideas to take away from all this? First, these tiny, microscopic forces have massive, massive real-world impacts. Second, remember that reservoirs are super complex capillary systems, not just underground lakes. Third, a really significant amount of water and oil is going to be permanently trapped by these forces, always. And finally, understanding this physics is the absolute foundation for modeling and producing energy.
Which kind of leaves us with a final thought, doesn't it? We've just seen how understanding the physics of the incredibly small is absolutely essential for solving a problem on a global scale. It really makes you wonder. As our ability to see and model these microscopic worlds gets better and better, what other giant problems are just waiting out there for us to solve?